Welcome back to the channel. In a previous video, I went outside into the wide world to show you how trigonometry can be applied out there in real life. Let's roll the clip.
As I was walking around, I came up to this other palm tree that looks even taller to me. It's even got a little flag on it. But unfortunately, this one is in someone's backyard, so I can't exactly get in there and figure out how far away I am. I can't measure how far away I am from it because it's in a backyard. But thankfully, thanks to trigonometry, I still have a chance. If I know the width of the street, which I already do, it's 27 feet wide, I can take one angle measure here on this side of the street and then another angle measure from the other side of the street, and I should be able to use those two angle measures together to figure out how tall this thing is, even without being able to measure the distance to it.
So here is a diagram of the situation. When I took the measurement from the close side of the street, I got a 40-degree angle using my clinometer that I had on my phone. When I backed up across the other side of the street, which is 27 feet away, and I took the same measurement using my clinometer, I got 32 degrees. Okay? Now, I'm looking for the height of the tree, but I also don't know how far away I was from the tree when I started. And then finally, my measurements are being taken from 6 feet up off the ground because I'm not like laying on the ground and using the clinometer. The clinometer is about 6 feet off the ground when I take my measurements. Okay, so that's our review. Let's actually solve this thing now. So you've got two different right triangles here, and I'm going to have to use them both. So I'm going to start by making a couple of right triangles, and we'll label them, and we'll go forward from there. Okay, so we've got this green right triangle, perfect, and we've got this blue right triangle, which is longer. Okay, this is not to scale clearly, although I can make it a little bit more to scale. Doesn't really matter. They're both right triangles, so I'll go ahead and mark them as such. Now let's go ahead and label these. So I went ahead and gave some variables here. H for height, X for the distance away from the tree. It turns out that I can find both. So just looking at this green one, I see that I've got a 40-degree angle here, and we're calling the bottom side X, and we're calling the height H. Okay? All I did was I took this triangle right here, and just like we did with similar triangles, I am extracting it from the diagram and making it its own separate thing so that it's easier to see. Now, how about the blue one? Well, I see that the angle for the blue one is 32 degrees. And I see that the height of the blue one is still H. And that's going to end up being what saves us. The fact that both of these very different, non-similar right triangles have the same height is going to be what ends up saving us. Okay, so now I've taken my diagram where it was me taking measurements from two different spots, and I have changed it into two right triangles. Now let's drop our SOHCAHTOA really quick. And the question, of course, is which trigonometric ratio do I use to solve this. Now in both of them, I missed something on my labeling. I did not get the long bottom side of this other triangle. So let's get that right now. Well, let's see. If this bit is x and this bit is 27, well, then the whole thing together has to be x plus 27. A lot of students have a really hard time coming up with expressions for things, but don't assume that just because there's an x, things work differently. They don't. If I knew that this side was, 10, if I knew that this x here was like 10, then to get the whole length, I would take that 10 and I would add it to 27 to get 37. I don't know what it is, it's x. So the total length is that x plus an extra 27. Again, a lot of students overthink this, and they seem to think that variables somehow work differently from quote unquote regular numbers. They don't. Okay, so it looks to me like we've got on both of these the opposite leg and the adjacent leg. In neither of these are we really caring about the hypotenuse. So that's tangent. Tangent is the one that has opposite and adjacent. So we're going to end up with two equations here, and we're going to sort of use those together. So we know that tangent of 40 degrees is equal to opposite over adjacent. Opposite over adjacent. H over x. And then for this bottom one, we get that tangent of 32 degrees equals, again, opposite over adjacent. H over x plus 27. Yes, there are two variables, but the setup is exactly the same as it's always been, and that's kind of the point I'm trying to make here. No matter how complicated these problems get, the basic idea is always the same. You're taking two proportions and you're setting them equal to each other. So now that we've got the proportions, I'm gonna get away from the triangles entirely, and we're just gonna look at these two equations, okay? So let's see. I get, on this top one, I'm gonna do some cross multiplying on both of these. So I'm gonna make them both over 1. And I'll do some cross multiplying. So I get, on this top one, h equals x times tangent of 40 degrees. And on this bottom one, I get h equals x times tangent of 32 degrees plus 27 times tangent of 32 degrees. Now, where did that come from? Because again, this tangent of 32 here, this tangent of 32, when I go to multiply it times x plus 27, I have to distribute it, right? I distribute it to the x times tangent 32 degrees, and I distribute it to the 27 times tangent of 32 degrees. Now, again, I could get a decimal at any time. I could plug tangent 32 or tangent 40 degrees into my calculator, get a decimal at any time, but I'm not going to do that yet. All right, I'm going to wait until the end. So now I have h equals x times tangent of 40 degrees, and I have h equals x times tangent of 32 degrees plus 27, blah, 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 blah. If both of these things equal h, then they must equal each other, right? If two things both equal h, and h is the same value, then those two expressions must be equal to each other. So we get x times tangent of 40 degrees equals x times tangent of 32 degrees plus 27 times tangent of 32 degrees. Again, nothing big, nothing mystical. I noticed that both of those equal h, so I set them equal to each other. Now, solving for x here seems like it's really, really difficult, but it's not. You see how I have an x here and I have an x here? I want to get those x's on the same side of the equal sign. Okay. Now we're going back to algebra here. At this point, this is kind of integrated math 1 stuff, but it's a complicated application. So stay with me. I'm going to subtract x times tangent of 32 degrees from both sides. Okay. Subtract it from both sides. And I end up with, now, not really a heck of a lot I can do to combine these. So I get x times tangent of 40 degrees minus x times tangent of 32 degrees. And that's going to equal 27 times tangent of 32 degrees, right? Over here on the right side, these two cancel, the positive and the negative. So we're just rearranging things a bit. Now notice that on the left side, well, hold on, I'm going to pause for a second. It looks like I'm doing a lot of complicated nonsense here, but what I'm doing is the same algebra you've been doing since probably 7th or 8th grade. You're just looking at that tangent 40 degrees and that tangent 32 degrees like it's something new, like it's something different. It's not. They're just numbers. This is the same thing if it was like 3x equals 5x plus 20 or something like that. The idea, the shape of it is exactly the same. The fact that we're using these weird numbers, tangent 32 degrees, tangent 40 degrees, doesn't actually change anything. So try not to let that confuse you. Now, here on the left side, I still have, you'll notice, an x here and an x here. Both of these terms are being multiplied by x. Now, here's an integrated math 2 thing. We learned that if you have the same factor in two different addends, in two things that are being added or subtracted, we can factor that out. So we get x times, well, x tangent 40 divided by x is tangent 40 degrees. Minus, again, we are dividing out that x, so we get tangent 32 degrees. And that still equals 27 times tangent of 32 degrees. That hasn't changed. Factor out the x. Now again, it seems like we've made it uglier, but we're actually only 2 steps away from getting the solution. And one of those steps is going to be calculator. So we've got x times this big, complicated, annoying looking number. But it's still just x times a number. We know what to do when we have x times a number. We divide by that number. So I'm going to divide both sides by this whole thing here. I'm going to divide both sides by tangent 40 degrees minus tangent 32 degrees. I don't know what that number is, but it is just a number, so I can divide by it. So I'm dividing both sides by that, and I get x equals 27 tangent 32 degrees on the top divided by tangent of 40 degrees minus tangent of 32 degrees. Again, I just divided both sides by the thing that's highlighted in red. You'll notice that it's the same thing that's down here. Okay? I'm just following the same rules of algebra that you have learned since you were probably in 7th or 8th grade. Now it's calculator play. All right? So let's see. I'm going to go to calculator. I'm going to make sure that I am in degrees. Don't forget that. We're going to learn about radians in a little bit. Now, let's see. 27 times tangent of 32 degrees. I'm going to use parentheses here. So I'm going to say 27 times tangent of 32, end parentheses, divided by, now what goes on the bottom? Tangent of 40 minus tangent of 32 degrees. Tangent of 40 degrees. Ooh, I need parentheses for this one too. Can I go back? All right, divided by parentheses. I want to make sure everything gets done in the right order. If I was doing this on a regular calculator, I would probably do it step by step, one step at a time. So it was, checking again, tangent 40 minus tangent 32. Tangent 40, end parentheses, minus tangent 32, end parentheses, end parentheses. So I'm going to stop for a second and make sure you understand why this is what it is. We're taking 27 times tangent of 32, that's the top. And we're dividing it by tangent of 40 degrees minus tangent of 32 degrees. Equals. Sometimes the camera gets in the way. There we go. 78.75 feet. 78.75 feet. So we're going to go back and we're going to say that x is approximately equal to 7. So we're going to go back and say that x is approximately equal to 78.8 feet. So are we done? Well, no. X isn't what I was looking for. Although it is kind of neat that I now know that I was 78.8 feet away from the tree when I took my initial measurement. That's good information to know. I could now use that with sine code or with tangent to figure out h. And in fact, we already have, because we see here that h is x times the tangent of 40 degrees. So we're going to say that h is approximately equal to 78.8 times the tangent of 40 degrees to find the height. Okay, back over to the calculator. Oh, hey, look, I already have the exact answer on here, so I'm just going to take that existing answer. I'm going to say times tangent of 40 degrees, end parentheses, equals 66.08 feet. So I get h is approximately equal to 66.1 feet. Now, is that the height of the tree? Almost. Remember that all of my measurements were taken from 6 feet off the ground, right? I did not lie down on my stomach, put the camera on the ground, and make these measurements. The measurements were taken from 6 feet up in the air, so we're going to take that, we're going to add 6 feet, And we're going to say that the tree is 72.1 feet tall. You can ignore these other problems for now. I'll do those in another video. In fact, I'll go ahead and, yeah. So I hope that you can see how powerful this trigonometry thing is. I wasn't even able to get a measurement of how far away I was from the tree, but because I knew how wide the street was, I was still able to take measurements and fairly accurately estimate the height of this tree in someone else's backyard that I had no access to. Now, again, this is a very complex problem. This is the kind of problem that you would see in an advanced worksheet or perhaps in an AP class. But it is important to see where these things can go, because out there in the real world, things aren't nice and neat like they are on a math worksheet. Things get messy, things get ugly, and you have to make some assumptions and make some estimations to solve real world problems with real world math. Anyway, I hope this helped. This is probably the most difficult kind of problem that you will see in right triangle trigonometry. And after this, we're going to move on to circles. So I'll see you next time. Class dismissed.